If annotators keep seeing easy pairs, your CRELs grow without getting smarter. Uncertainty sampling with scikit-learn sends them the results the model genuinely cannot decide. You'll score the pool with logistic regression probabilities and use uncertainty sampling to pick the query document pairs nearest the relevance boundary to label next. I'm Professor Pi, teaching search and IR with simple Python. Labeling relevance is expensive. Teams often have thousands of query document pairs, but only a few hundred judgments to spend. Active learning helps you put those judgments where they actually change your model. It sits between your retrieval signals and the human assessors, and aims to turn budget into better learned boundaries instead of wasted repeats. Think of active learning as asking the model where it hesitates. If the model is very sure a pair is relevant or not, that label teaches little. If it's on the fence, a single judgment can shift the decision boundary. A tiny initial seed plus a large pool of unjudged pairs is enough for the idea to work. We will build a tiny loop you can run on screen. It will hold a small set of judged pairs, a larger unlabeled pool, and a logistic boundary that scores uncertainty. You will see how picking the most uncertain pairs focuses labeling effort so the model learns faster and with fewer labels. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now, let us make the smallest working dataset to show the mechanics. This snippet builds the smallest active learning setting, a tiny set of judged pairs, and a larger pool waiting for labels. The labeled rows include a query ID, a short document queue, 2 interpretable ranking features, and a binary relevance judgment. The pool rows match that feature shape, but lack labels. That's exactly where your labeling budget gets spent. The feature values stand in for signals an IR researcher might already have, like a neural margin and a sparse matching score. The visible output shows how many pairs are still unjudged, which is the budget pressure active learning will target. Next, we sanity check whether the seed judgments contain any signal at all. This example checks whether the seed judgments contain a usable relevance signal before training anything. X extracts just the feature vectors, while Y holds the binary query-style labels. The code compares the first feature's average for relevant versus non-relevant rows as a quick sanity check on separation. It isn't a replacement for proper evaluation, but it catches the common failure mode where the seed set is too noisy or too flat to guide selection. The visible output shows a clear margin gap, which makes the next probabilistic ranking step meaningful. With a sane seed, we fit a probabilistic model that can say how uncertain it is for each pair. This code turns the seed quels into a probabilistic boundary model using scikit-learn logistic regression. Ranker.fit x, y learns from the judged pairs, and predict proba scores each unjudged row in U as relevant or non-relevant. Rel-col protects the code from assuming a fixed class column order, so probs always selects the probability for label 1. Fit intercept equals false keeps the tiny demonstration centered, making the boundary case visually obvious. The visible output shows the pool contains a pair right at the model's decision boundary, which is where a new judgment can be especially informative. We then convert those probabilities into a concrete policy for which pairs to send to assessors next. This snippet converts scikit-learn probability scores into an explicit labeling policy. Pairs near 0.5 get high uncertainty, while very confident positives or negatives move down the list. Order sorts the pool by uncertainty first and uses the query ID as a deterministic tiebreaker, which keeps the displayed batch stable. Batch is deliberately small because active learning is about spending the next few judgments well, not labeling everything in sight. Increasing the batch size would improve throughput, but may include less informative pairs. The visible output names the next pairs to send to assessors, focusing effort on boundary cases. Finally, we simulate getting back those labels and show how the model updates. This example closes the active learning loop by turning the selected batch into new queries and retraining the scikit-learn logistic regression model. Batch rows represents the assessor response. Here, the labels are simulated only, so the tutorial can run end-to-end on screen. Labeled 2, x2, and y2 rebuild the training set with the newly acquired judgments. Then regfit refreshes the boundary. Krells keeps just the incremental labels that would be merged into an evaluation pool or training file. The visible output shows the new judgments produced by one active learning round, completing a compact baseline for budget-aware relevance labeling. On screen, this toy loop maps cleanly into real work. Replace the synthetic features with a neural similarity margin and a BM25 score, and swap the tiny pool for a streaming set of recent queries. The same pick uncertain strategy will concentrate assessor time where models disagree. It's a labeling loop that asks for the pairs the model finds most uncertain. Use it when you have a limited human labeling budget and want faster model improvement. One caveat: if your seed labels are noisy or uninformative, the method will stall, so check separation first. A useful next step is to replace the logistic model with a richer scorer, or to add a second feature like BM25. Then compare how many labels each variant needs to reach the same validation accuracy on a held-out set. If short, practical IR helps, subscribe and watch the IR videos.